Okay, so we'll be starting with the session now. Hi everyone, this is Manish Nath from Hex-Star Universe, and I'll be your host for today's session. First of all, thank you everyone for joining us today. Today, Hex-Star Universe, in collaboration with SS Citizen Science Group and Kalimpong Science Centre, has brought to you a session named Decoding the Mysteries of the Universe, Dark Energy, and Dark Matter. And to enrich us on this topic, today we have none other than Mr. Anshuman Baruah with us. He is a PhD research scholar in the Department of Physics at Albert Einstein School of Physical Sciences, Silchar University, Assam. We are really glad to have him here with us today. So without any further ado, I'd request Anshuman sir to proceed with today's session. Thank you, everyone. Okay, so we can start with the session now. Hi everyone, this is Manish Nath from Hex Universe, and I'll be host for today's session. First of all, thank you everyone for joining us today. Today, Hex Universe, in collaboration with SS Citizen Science Group and Kalimpong Science Centre, has brought to you another session named Decoding the Mysteries of the Universe, Dark Energy, and Dark Matter. And to enrich us on this topic, today we have none other than Mr. Anshuman Baruah with us. He is a PhD research scholar in the Department of Physics at Albert Einstein School of Physical Sciences, Silchar University, Assam. We are really glad to have him here with us today. So without any further ado, I'd like to request Anshuman sir to proceed to this session. Thank you, everyone.
Thank you very much for the introduction. And apologies I was having connectivity issues. I'm sharing my screen, should be visible in it. Hi, can you see my screen?
No.
No, sir, it is not visible.
I'm extremely sorry. There's some connectivity issue here. I'm, rejoining the meeting and trying to share my screen once again. Please give me a minute. Okay, I hope my slides are here now. Am I audible and are my slides visible?
Yes, sir, you're audible and your screen is also visible.
Okay, thank you so much. I was having some major connectivity issues. Please let me know in the chat box, if there are any connectivity issues in the middle of the talk. So apologies for the delayed start. My name is Anshuman, and I thank the organizers here at Hex-Star and SS Citizen Science Group for having me once again. The last time we met a couple of months ago was when we talked about black holes and wormholes, and today we are here to learn the story of the dark universe. Now, before I begin, I noticed in the registration list that several people from higher education institutes have been joining, have been registering for the event, and it's a very good thing. But please know that my talk today will be directed at a very, very general audience. Those of you who might be, students of, say, masters or above in physics, and you might have, other advanced queries or, topics or discussions that you would like to have. I would be more than happy to, address them when we have the discussion at the end of the talk. So let us begin with the very, beginning of the universe itself. So we are all familiar with the Big Bang hypothesis, and here's Sheldon Lee Cooper smirking at me as I try to explain this infinite cosmos to you. So of the Big Bang, explain modern cosmological theories, but there are some problems in cosmology. So those of you who are younger ones in the audience, and you might not be familiar with the term cosmology, because as it turns out, it is not as famous as the word astronomy or astrophysics, right? So it comes from Latin. Cosmo means the world, and logi means to study. So it's basically the study of the whole cosmos. So there are some problems in modern cosmology. Now, if you go on and ask cosmologist who is a professional, he will tell you about other things when they talk about problems in cosmology, but I will be talking about the general stuff. So a few problems in modern cosmology are, firstly, the issue of inflation. So as the Big Bang started, the universe, it expanded exponentially in size. So how did that happen? We currently do not have a very good idea, although we have several theoretical models, and hundreds and thousands of people are working on it. We do not have a concrete idea. The second problem that we generally encounter is the issue of dark energy. This is what we will be addressing today. And the last is dark matter. So yeah, we will not be talking about inflation today. That is in itself a very, very vast topic. We will be talking about dark energy and dark matter. So as it turns out, there are different ways, to estimate the content of the universe. I will go through some of these ways as I, walk you through what dark energy and dark matter are and why they matter. As it turns out, most of the universe we cannot even see, we cannot even measure. So you and me, we are made up of atoms and molecules, right? So these atoms in turn are made up of what we call baryonic matter, what we call baryons, the protons and neutrons that make up the atoms, the electrons as well up to some point. So as it turns out, this general or ordinary matter, it makes up the tiny fraction in the circle that you see. The blue fraction, it roughly accounts for a little less than 5% of the entire content of the universe. The big black patch that you see over there, it accounts for approximately 70% of the universe that we can measure. That gray shaded area, it is basically what dark matter gives a contribution to the entire mass and energy content of the universe. So after all of these developments in modern physics, we still don't know what, collectively more than 70 and 26% of the universe are actually, we don't know what they're made of, right? So this is the problem that I'd like to address today in my talk. So when we talk about cosmology, the most accurate modern cosmological theory we have is what is known as the lambda CDM model. Now, this symbol lambda is what is known as the cosmological constant. It comes from Einstein's theory of gravity. We will discuss about lambda in detail in the upcoming slides. And CDM stands for cold dark matter. So this particular model, it explains, why the universe is expanding. It explains what is the matter that we cannot see. There's the matter content that we cannot see in the universe. So this is a reasonably good model. It can, explain how the cosmic microwave background works. And please don't worry about it. I will explain all of these terms as I, go on to explain to you in detail what these things are. So this theory gives reasonably good predictions for the cosmic microwave background. It tells you how large scale structures, galactic clusters and, filaments and whatnot, how they form. And it also can more or less explain to you why or how dark energy basically works in the universe. So, however, the lambda CDM model also has some flaws in it, and we will delve into it deeply. But before that, let me introduce you to part one of my talk. So, the part one of my talk is called the why and how of dark energy. So, the story started like this. So, Newton's theory of gravity reigned supreme for several hundreds of years. And then, starting in 1905 and until 1915, Einstein came up with some radical ideas. So Newton's theory basically told you how gravity works, right? So most of us who are above, class 7 or 8, we have studied, Newton's law of gravity. In case some of us don't remember, it's okay. But Newton's law of gravity, it basically tells you how gravity works. It does not really tell you why is it that gravity works? Why is it that there is a force of gravity? So Einstein revolutionized this idea. He first introduced what is known as the special theory of relativity. We'll not get into that because it's going to veer off topic. And then he developed a general version of the theory, which explained gravity as an outcome of the curvature of space-time. And how I'm pretty sure all of you have seen, internet videos and animations of, how if you stretch a bed sheet or if you stretch a big rubber sheet and you put a heavy metal ball in between, it curves the fabric of the bed sheet or the rubber sheet, right? So although it is not a very, very accurate analogy, that is basically how the presence of weight or mass in space-time, it actually curves the very geometry of space-time itself. So till date, even after more than a century of its formulation, Einstein's general theory of relativity, it stands as one of the most well-tested physical theories of all time. Then came four people. These FLRW are basically names of four people: Friedman, Lemaitre, Robertson, and Walker. So what these guys did is that, in fact, Einstein had significant contributions in that as well. They tried to solve the equations of Einstein's theory, right? And they tried to solve this system of equations for the entire universe. And these are what we know as the cosmological solutions to the Einstein's equations, or we call them the FRW or FLRW solutions as well. Then in the late 1920s, came the famous astronomer Edwin Hubble. So as some of you might know, the famous Hubble Space Telescope is named after Edwin Hubble. So Hubble was basically the one of the first persons to realize that galaxies, our galaxy, he was one of the first persons to realize that our galaxy is not actually the only one, and there are thousands and perhaps millions of other galaxies present in the universe. And when he tried to measure, the light coming from these galaxies, what he found that galaxies that are far away from us, they are moving away from us. And the funny part was that galaxies that are farther away, they're moving away from us at a faster rate. So it was a startling discovery. Einstein initially himself did not really like the idea of, the universe expanding away from us in all directions. Then, in the late 1990s, there were two experiments that were going on in different parts of the world. And in 2011, Perlmutter, Schmidt, and Rice were basically awarded the Nobel Prize for their 1998 discovery, where they improved upon Hubble's predictions. So Hubble said that the universe is expanding away from us in all directions, and these people, they discovered that the universe is not only expanding, but it is expanding at an accelerated rate. So why is this accelerated expansion happening? People have been trying to figure out why this thing works, what is the physics behind it since the late 1990s. So this particular accelerated expansion is basically caused by dark energy. But how does dark energy cause accelerated expansion? Let us take a quick look. So it all starts with this guy again, right? He's still teasing us because we're still trying to figure out the mysteries that he, developed 100 years or so ago. So what Einstein did is that he wrote down an equation that looks like this. And please bear with me. I will try to avoid mathematics as much as possible. In the 30 or so slides that I have prepared for you guys today, there are only 2 slides with mathematics, and this cannot be avoided. And if you do not understand what this symbols and this confusing stuff is, don't worry about it. You don't need to understand. I will tell you whatever it is that you need to understand, right? So this particular equation here was, developed by Einstein. So this particular equation can explain everything from black holes to the entire universe. So as I have said before, when people try to solve this equation, one of the solutions, it looks like this. This is basically the first of the 3 FRW equations or FLRW equations. So there is some interesting stuff going on in this equation, right? Let me highlight some for you. Okay. So this part, basically, it tells you what the density of the universe is. So this little a's that you see here, these are what we call the scale factors, right? They tell you how the geometry of the universe is changing. And this entire part, as you can see, it looks like 0. It looks like it should be greater than 0. It's a positive term, right? And on the right side, if you see this particular thing, this thing can take values. This thing can take values of +1, -1, and 0. So if I plug in these 3 different values, I get 3 different kinds of universes, right? So if say k is +1, what happens is that the geometry of the entire universe, in a very simple sense, the universe will look like a sphere. It will look like a ball. So if you try to measure angles of a triangle on a ball, it will add up to more than 180 degrees. So the geometry becomes different from what we have learned in school, right? Say, for example, k becomes -1. What happens is that the universe doesn't look like a ball anymore. It looks like a saddle, the one that you would, put on a horse and ride away. But if it is 0, we get a flat universe, and we have good observational evidence to, conclude that this k is very, very near to 0. Because whenever we look all in different directions in the universe, we see that the universe is homogeneous and isotropic, which is a funny little way of saying that the universe looks same all in any direction that you look, and it contains more or less the same stuff in any direction that you look, right? So there is this constant dance between the left-hand side and the right-hand side of the equations. But people realize that if this equation were to hold, then the universe should continue expanding forever. Einstein didn't like that idea. At that time, Einstein used to subscribe to the opinion of a static universe. So what he did was, he introduced a term called lambda into the equations. Now, mind you, this term has to be introduced in this equation first, and then when you solve it, this particular blue equation that you see here, it changes. You see there is a new term that has been added here. So the original idea for adding this term was to, balance out the contracting behavior of gravity, But this particular term has far-reaching consequences. This lambda is basically what we will interpret as dark energy. And how do we do that? I'll get into it in the next slides. So this term basically leads to expansion. If there is a God, perhaps he has said, let us put in a lambda in the equations and let there be expansion. Fine. So how do we know that the universe is expanding in the first place? So how did this team in 1998, they discovered that the universe is expanding? So they looked at what are known as type 1a supernovae. So some of you might know what a supernova is. For those of you who do not know what a supernova is, let me tell you. So when stars that are very, very much heavier than our own sun, when they die, why do they die? You might know that, that stars, they burn hydrogen inside of their cores, right? So if they run out of hydrogen, what do? They start burning helium, and so on and so forth. They keep on burning different kinds of gases, different kinds of elements. And at some point, some funny physics comes into play where the core of the star is no longer hot enough to, sustain fusion of heavier elements. So usually what happens is that the star will burst out. These supernovae are so bright that even if you look at a supernova that is coming from a galaxy that is millions or billions of light years away, the light from one particular supernova will actually outshine the entire galaxy itself, right? So there's something special about type 1a supernovae. So these are known in astronomy as standard candidates. By standard, I say that the brightness that you see from the source, it will be constant. So if there is a type 1a type supernova anywhere in the universe, we will always measure a particular constant intensity. So there are other different standards in astronomy as well. Another example will be Celsius. So what this thing did in back in 1990, light
Your
coming
voice
from
is not clear.
Sir, I think you are facing some network issue, so your voice is not clear.
Okay, is my voice okay now?
Yes, sir.
Okay, the screen is still up, right?
Yes, sir. The
Okay,
screen
fine,
is
yeah.
visible.
So I don't know where I lost track. I mean, where my voice started cracking up, but we were talking about type 1a supernova, and I was telling that these things have constant brightness. So no matter where in the universe we see a type 1a supernova, it gives constant brightness. So this diagram on the right, it basically shows you how a type 1a supernova works. Usually, white dwarf, or sorry, pardon me, usually a brown dwarf, a white dwarf is orbiting another star, it swallows up matter, and once it has swallowed up enough matter, it cannot sustain itself anymore and it explodes. So some teams in the late 90s, they tried to measure the light coming from these sources. And what they measured is known as the redshift. So what happens is that as light travels to us here on Earth from far, far away galactic sources, the light loses energy, right? So as the light loses energy, it shifts from the blue end of the electromagnetic spectrum to the red, meaning any color of light that you see being emitted from very far away in the universe, it will tend to become more and more red the farther away the object we are observing is. What they observed was that the redshift was actually more than what they expected. How can this happen? So let me recap just a little bit. The light from this different distant supernovae were measured, and they were expecting that the light will slowly turn red because they're reaching us from very, very far away sources. But when they did the measurements, they found that it is more redshifted than expected. The only possible explanation for this is that the space itself between the distant supernova and us here on Earth is expanding. And because of the expansion of this space, the light itself gets stretched out more than what it is expected. So this is how basically we can measure the expansion of the universe using standard candles in the form of type 1a supernovae. There is further evidence for dark energy. Let me highlight some evidences for you. So this schematic basically shows you a timeline of the entire universe. So at the very bottom, we have times reaching 10 to the power minus 43 seconds. And below it lies what we call the Planck era. That is when, things were so small that current models of physics cannot explain what goes on when some things become so small and so energetic, right? So finally, as the universe progressed, so something very interesting happened around 380,000 years. And this particular timeline is what I wish to discuss in order to explain better, in order to convince you that dark energy is something that actually exists and it is very, very real. So what happened in this time is called recombination. What is recombination? Let us take a look and how it tells us about dark energy. So when the universe first started out, if you see here, so there were protons and neutrons present. So some funny physics was going on and protons and neutrons were formed. But what happened was that the electrons could not combine with these protons to, form hydrogen atoms or to form any kind of atoms, basically. Because the universe was so hot that the electrons did not have enough energy to combine with protons to form, atoms. At that time, the universe was basically opaque, meaning you cannot see through it. Light cannot propagate through the universe. So what happened at this time was that electrons were free to scatter off photons. By that, I mean that electrons used to collide with photons, right? And finally, as the universe gradually cooled down, this temperature becomes suitably low for the electrons to combine with the protons and become hydrogen atoms. So the first hydrogen atoms were formed 380,000 years approximately after the Big Bang. And then what happened to these photons? These photons, they were freed up. The universe became transparent. So let there be light, right? So the first light in the universe comes from around approximately 380,000 years after the Big Bang. And today we can still see this light actually. Everywhere you look in the sky, you can still see this light. So initially when this light was released, the energy was so high that it was released as gamma rays. But since the energy has been lost and since the universe has been expanding ever since, this light has again redshifted, as I had explained before. And now we can see it in the infrared region of the spectrum, right? For those of you who might get confused about what infrared is, this is the very, light source that is used to control TV remotes or in night vision cameras and security cameras and stuff like that, right? So we can still see this light. So this first light in the universe is what is known as the cosmic microwave background. So I have stacked three images here. So this cosmic microwave background was predicted in the late 1960s and people have been trying to measure it ever since. And this is from the Kobe experiments from the early 90s. So this is from the Wilkinson microwave anisotropy probe in 2003. And this is the most recent and most advanced measurements of the cosmic microwave background. So the different colors that you see here are basically different temperatures. You can interpret it as temperature. The redder ones are hotter regions, the bluer ones are colder regions. Now, when I say hot and cold, you can also correlate this to the amount of matter and energy that is present in the universe when you look up at the sky and you see the CMB. So if you can see, if you look at this map carefully, you see that it is not even, right? There are some regions that are overly red. There are some regions that are overly blue. Why is that happening? In physicist terms, we call these anisotropies. Anisotropies meaning irregularities in the cosmic microwave background. And these irregularities in the cosmic microwave background, they are very important to understand both dark matter and dark energy. In the context of dark matter, I will get into it in the second part of my talk. Let us see what we can learn from it about dark energy. So this is very intrinsically related to another event, the first sound waves in the universe. Before there were even helium atoms, there were sound waves in the universe, the first of them, in fact. So how did these sound waves come to be? So as I have just explained, protons and neutrons, they combine with electrons approximately 308,000 years after the Big Bang, and the first light was released, right? So before this light was released, what happened was that these light quanta, these photons, they used to exert a tremendous pressure on the hot plasma of protons and electrons, the hot subatomic plasma that was present all around it. The light that was freely traveling around, it used to exert an enormous amount of pressure. But when recombination occurred, when electrons combined, suddenly this pressure gradient disappeared and the shock wave was formed. This is a bit difficult to explain for someone who doesn't have basic knowledge of physics, but I'm trying my best to make you understand. If you have any doubts further, I'll be more than happy to discuss it in the discussion section, right? So what happened was that these shock waves that were produced, they were imprinted in the very fabric of space-time. Let me try and play this graphic for you. Okay, fine. Yeah. So if you look at the graphic, there were density fluctuations in the early universe and shock waves were created. And these shock waves, as it turns out, they happened at different instances of the early universe. Now you have to keep in mind that the universe was very, very small at this point compared to what it is today. And these kind of fluctuations or shock waves or acoustic waves, as we call them, they occurred in various places in the universe. Now, as the universe expanded, the velocity of sound decreased. Back in the early universe, it was around half the speed of light. And as the universe expanded and cooled, the velocity of sound decreased and these waves got frozen in time, right? And you'll be shocked to see that most of the galaxies were actually formed around these rings, around these shock waves of rings that were actually remaining from the early universe. Now, what we can do is that we can take galaxies, right? And we can measure the distance between the galaxies. And we can map out how far apart these galaxies are and at what distance, how many galaxies they occur, right? So if I do this, if I keep on doing this for sufficient number of galaxies, so these green bars, we are taking the distance between galaxies, and now we are counting how many galaxies are occurring at each distance, right? So we can keep on doing this for a statistically significant number of galaxies, and if we keep on doing it for hundreds of thousands of times, we will obtain a pattern. And this pattern is very, very special. So this pattern that you see here, it correlates exactly with the cosmic microwave background anisotropies that I showed you in the maps in the previous slides. So this animation is curated from Castro. You can check out his YouTube channel. He has got very interesting physics animations. So these baryon acoustic oscillations, they basically tell you that the universe expanded. And this is why this expansion froze these, oscillations or these waves in space. And along these waves, galaxy clusters formed that we can still see in the modern universe. So I have given you two hopefully compelling arguments regarding the existence of dark energy. But what exactly is dark energy? We still haven't talked about it yet, right? So is it the cosmological constant? Because I told you that the most acceptable cosmological model is the lambda CDM model, and it has lambda in it, right? The cosmological constant in it. So as it turns out, there is a big catastrophe, and I'm not just using this word catastrophe as a comic pun. It is actually what is referred to in modern literature as the vacuum catastrophe or the cosmological constant problem. The problem arises when we try to actually measure what is the value of the energy density of the vacuum itself. What is the energy that is inside the vacuum that is actually creating this lambda, which is actually giving you the accelerated expansion of the universe. So if we try and measure it, we end up in a catastrophe. But before that, let me tell you why I suddenly started calling this a vacuum energy instead of calling it the cosmological constant. So you could have asked me, what exactly is the cosmological constant? Okay, sir, the cosmological constant is driving the expansion of the universe, but what is it exactly? So after this lambda thing was proposed, several decades after it, quantum field theory was developed alongside it. And people realized that in quantum field theory, the vacuum is not static. So usually what do we understand when we say a vacuum, right? Nothing should be present, not even a single air molecule And in fact, we were in fact taught in school, right, that the space between stars and between planets is basically a vacuum. There is nothing in it. But as it turns out, it is not. Even if you can develop the most sensitive and powerful pump in the world, and if you try to pump out the air and everything that is present inside of a closed box, you might say that, okay, I have created a perfect vacuum, there is nothing inside of it, but there will still be something inside of it. The vacuum itself has an energy. This energy pops out of nowhere, it comes and disappears, and these fluctuations basically, when you integrate them, when you add them up over large and large distances, it gives you an energy density of empty space-time itself, meaning that space-time itself has some sort of energy. So this particular energy is what is manifested as the cosmological constant in the lambda CDM model. However, if we try to make theoretical calculations regarding what the value of this energy is, and if we try to measure it, there are some techniques. If we try to measure it, the two observations, they deviate embarrassingly. It is one of the most, biggest conundrums or clashes in modern physics. So there is some problem with the concept of dark energy as the cosmological constant. Let us see how we can solve it. So is dark energy some kind of anti-gravity effect? Because the universe is full of matter, right? Matter exerts gravitational force, and gravity tends to pull everything together. But we have all been talking about things repelling each other, things going haywire, being pushed away from each other. So we have to look at another equation for it. And please bear with me. This is the only slide left that has any kind of math in it. So the first solution to the Einstein's equations of gravity that I showed you was incomplete. There is another story to it. So the another story comes from the second of the Friedman equations. So if you look at this particular equation, this particular thing is known as the density, and this particular thing is known as the pressure. Let us forget about these fellas for as of now. So this thing tells you how the universe is behaving geometrically. This thing tells you how the matter content of the universe is behaving. So again, there is a constant dance off here. So if we include the lambda into this equation, we see that we have a positive term that is coming out here, right? So this positive term, as it turns out, it ends up balancing the negative term that is sitting right here. Let us see how it does that. So by the way, and this entire equation, it is dependent on time. All of these values that you are seeing, these values, they will change with time, meaning as the universe grows older and older, these values, they keep on changing. In the early universe, these values are different. In the current age, these values are different. So what is happening in the current age? So when I write the future here, I'm actually talking about the current age of the universe. So this term gets absorbed into these factors, and this energy density of matter is replaced by the energy density and pressure of dark energy itself, meaning that the energy and the pressure exerted by dark energy, it becomes more than that exerted by normal matter and normal energy, right? Things that we can see and we can feel and we can measure, like stars and galaxies. So this is the particular era of the universe we are in. So this is what we call the dark energy dominated era. This is why the universe is expanding at an accelerated rate currently. However, the funny part is that dark energy possesses negative pressure. So this negative pressure is something that is very, very hard to explain intuitively. Even us physicists have a hard time grasping it when we encounter it in our calculations. If you're interested in knowing more about it, I'll be happy to answer your questions as the session progresses. So what may possibly cause this anti-gravity type effect, right? So in the lambda CDM model, the most accurate model of modern cosmology, it tells you that the dark energy basically is lambda. But I told you that there is a very big problem in lambda in that what we calculate theoretically and what we can measure observationally, there is a big difference in it. So we physicists will look for other explanations. What may possibly cause this anti-gravity type effect? What may possibly cause this negative pressure unphysical kind of an effect? So there are many ways that you can approach this. One of the popular approaches in current literature is what we call modified gravity models, where we modify Einstein's gravity. But I would like to direct you to what we call quintessence in cosmology. So quint meaning five, essence meaning fundamental, constituent type of a thing. This comes from Latin derivatives. So quintessence basically can be interpreted as an additional force, right? So you know that there are different forces in the universe, right? There is the electromagnetic force, there is the weak force. We call them together the electroweak force. There is the strong nuclear force, which basically tells you how things behave inside of atoms. And then there is gravity. We are saying that there may be another force in the universe, which is quintessence, which is carried by a field. So quintessence has this peculiar property of negative pressure. So if we do calculations for cosmology, if we do calculations for black holes and wormholes, we frequently encounter physical things that resemble quintessence. So this is an active area of study that people are developing, considering the fact that it can explain the accelerated expansion of the universe. So I would like to, because this is a very, very vast topic. If I keep on speaking, I can go on for one whole day about dark energy itself. But to make it short, I am transitioning to the second part of my talk. So the part 2 of my talk concerns itself with the whys and hows of dark matter. Okay, let's delve on. So what does a galaxy and the Ferris wheel have in common? I'll give you a moment to think about it. They spin. Both of them, they spin. Now, if you ask me, why does a galaxy spin? The question is a bit complicated. It has got to do with conservation of angular momentum. We can talk about it later if you want. But both of these things, they spin. One of the reasons why the galaxies are spinning is because of the mass that is present in the galaxy, right? In the form of stars, in the form of planets, in the form of interplanetary gas and dust. But when we try to measure how fast these galaxies are moving, right, we get something very, very peculiar. So this dotted line that you see is the, by the way, in this axis, we have the velocity, right? And here we have the distance. And if we try to estimate theoretically the speed for how galaxies should move, theory tells you that you get a curve that looks like this. But if we measure observationally, there are various types of ways that we can measure the rotations of galaxies. That is a whole different topic. But if we measure, you see that these two graphs, they look significantly different, meaning that the galaxies are spinning much, much faster. In fact, they're spinning so fast that they should eject out all of their stars and lose stability. But that is not happening, right? This calculation, it considers the matter that we can see, meaning all of the stars, all of the gas and dust that is present in the galaxy. So if that was the only mass present, this is the velocity that we would have obtained. But we are obtaining very, very high velocities, meaning there is some additional mass present in it. This particular fact was noted. This gentleman here was one of the first people to basically notice that there was something wrong going on. So this is Fritz Zwicky. So Fritz Zwicky actually was a Swiss astronomer who realized that something odd was going on, and he called it Dunkelmaterie, which basically translates to dark matter. But this was long before galactic rotation curves were measured. There's a whole different story where he got this idea. You can read about it. It's quite interesting. He was actually also measuring what is known as the coma cluster. But this idea was actually overlooked until a long, long time after, Zwicky initially used the term dark matter. So the first discrepancy is that there is more matter present that we cannot see. When we look at galaxies, we see stars and we see dust, but there is something else present that is making the galaxies spin faster than they should be spinning. Okay, fine. What is another evidence that we can look for dark matter? So we can look at gravitational lensing. So those of you who don't know what a gravitational lensing is, what happens is that when you are when we are looking at something very, very far away in the universe, and that is very massive, meaning it has a very, very high gravity, light coming from behind that particular object gets bent around it. So we can calculate gravitational lensing for galactic clusters. By galactic cluster, I mean collections of galaxies that are held together by gravity, right? So if we try to measure the gravitational lensing from distant galactic clusters, and if we try to compare it with our calculations, if we consider the mass that we can see and if we calculate, we find that the gravitational lensing is anomalous, meaning there should be more mass to account for the lensing that we are seeing. This is another stark evidence for the presence of dark matter. So what is going on then? Galaxies are spinning faster than they should be. Gravitational lensing is occurring more strongly than it should be. All of these, they suggest that there is some additional matter present which we cannot see, right? So let us look back. Are we wrong? Is our theory of gravity wrong, right? So we are familiar with Newton's laws, and we know that Einstein further generalized these laws, and now all of our understanding is based on these particular laws. So I'm questioning, is my understanding of gravity wrong? So does gravity work fine when we are throwing a ball, when we are flying an airplane, or when we are, sending satellites into space, when we are sending probes into the solar system? The question that we can ask is gravity, are our laws of gravity all right up to such small distances, but do these laws, they break down when we move to greater distances, like say hundreds of parsecs or millions of light years? That's its distance that is present between galaxies and galactic clusters, right? So this idea was explored by physicists for a long time. In fact, this is still a very, very active area of study, and this is what is known as modified Newtonian dynamics. So a very simple way of understanding is this would be that the Newton's equations, they change, like I've shown you in this particular little graphic. Forget about the terms that you see there, but basically the 1 by r square behavior of Newton's gravity, modified Newtonian dynamics says that as you go over to very, very large distances, so this behavior approximates a 1 by r behavior instead of a 1 by r square behavior. This is one way to look at it, right? So we might consider that our understanding of gravity is wrong. Perhaps at very, very long distances, gravity behaves differently. Or you may ask, is the standard model incomplete? For those of you who do not know what the standard model is, the standard model of particle physics is basically a theory of everything except for gravity, which is also a very interesting story we may explore some other time. So everything starting from the clothes you are wearing, from the water you are drinking, to what is going on inside of stars and galaxies and black holes, more or less can be approximated by standard model. It is a theory of subatomic particles. It tells you how many different kinds of particles are there, how many different kinds of forces are there, and how they are behaving. But there is a problem. Gravity does not work with standard model. But that is not important here. The question that I'm asking, is standard model incomplete? So galactic rotation curves tell you that there is matter that we cannot see, meaning it does not interact with light, it does not emit light, we cannot see it. Gravitational lensing tells you that there is additional mass that you cannot see. So is standard model incomplete? Meaning, can matter take different forms which we cannot see, which do not emit light, but they only exert gravity? Both of these are equally possible opportunities, but I'll tell you that we physicists have a preference for the other one. Recently things are changing, so this is a very recent development, and I would like to direct you to this particular issue. So let us consider the bullet cluster, right? The bullet cluster is a cluster of galaxies. Every single dot that you see here, apart from the star that is burning in front, these are galaxies basically, like our own. These are galaxies like our own Milky Way, and these galaxies, they clutter up, they form clusters, they dance together. And sometimes what happens is that these galaxies, they collide. These galactic clusters, they also collide. So when galactic clusters collide, we know that normal matter, they interact with each other, right? You push your friend, he gets hurt. Similarly, when two standard model particles, they collide, they interact. We say that they scatter. So we expect that if such big colossal structures that are millions of light years across, when they are colliding, we have known laws of physics that can predict the behavior. The predicted behavior says that the gas and dust, and mind you, this gas and dust, it also constitutes stars and even individual galaxies as well, right? So normal intuition would tell us that these hot gases in the galactic clusters, they will interact, and then dark matter should be left away, right? Because dark matter does not interact. It does not interact with standard model particles. It does not emit light. Okay, let's test this hypothesis. Let's see what happens. So I have a little animation here. God, I'm having trouble. Yeah. So this is the behavior that we would expect, right? Okay, now I would like to pause here and I would like to draw your attention. See, if dark matter was normal matter, right? Meaning, if our theory of gravity, if our understanding of gravity was wrong, or suppose if our understanding of the standard model was not correct, what we would have expected that as these galactic clusters they pass through each other, then this dark matter should have interacted the way hot gases did, right? Dark matter should have interacted with itself and they should have gotten all jumbled up. But when we did actually observe, what we observed is that dark matter was left in its place. So this is an actual image of the bullet cluster. It shows you the measurements that were done using gravitational lensing. We can measure the gravitational lensing and we can then calculate how much matter is present in what different parts of the clusters after they collided. And this is the result that we obtained. This is the result that we obtained. This is quite shocking. This is quite shocking for two reasons. Because if modified Newtonian dynamics were true, meaning if gravity behaved differently at different regions of space-time, what we would have expected is that the gravitational lensing at these regions would have been predicted exactly by interacting dark matter, but they do not interact. We see that the hot gases, they interact from two clusters and they're left at the center. But the blue exaggerated region, it basically tells you that there is more matter present here than there is in this center space, meaning that the dark matter that was initially surrounding the original galactic clusters, they pass through each other without interacting, meaning our understanding of gravity is not that wrong, meaning Einstein is inevitable. He stands corrected. He does not stand corrected, pardon me, he stands inevitable. Okay. There is another very, very compelling proof where we can probe these ideas like modified Newtonian dynamics and beyond standard model physics. So we can look at what we call ultra diffuse galaxies. So ultra diffuse galaxies are basically galaxies that have very, very low amount of stars and dust and gases. Like compared to Milky Way, it would be very, very few tenths of a percentage, the number of stars present in an ultra diffuse galaxy. So what astronomers very, very recently did was that they measured the rotation curves for the ultra diffuse galaxies, right? And they found that these ultra diffuse galaxies, they contain no dark matter. How they know? They measure the galactic rotation curves. So when they measure the galactic rotation curves, they see that the curves can be explained without any dark matter. But then this might confuse you. I was trying to prove to you that dark matter exists, and now I'm saying to you that there are galaxies that can live without dark matter at all. But this is actually a more conclusive proof that dark matter exists. Do you know why? Because if dark matter was originating from a fallacy in our understanding of gravity itself, then dark matter and normal matter could not have been separated. They should not be, we should not have been able to separate them, meaning there should have been no galaxies without dark matter. So this is a very, very puzzling development. People are still very, very actively working on it. People do not have any conclusive idea based on my knowledge as to why such things happen. So one of the ideas is that, massive galaxies, they may collide and the dark matter may pass right through, and this collision may eject, significant portions of stars and gas and dust from the host galaxies, and they end up forming ultra diffuse galaxies without dark matter. There is also an opinion that active galactic nuclei, meaning, gigantic supermassive black holes in the centers of some galaxies, they may behave so violently that they may eject some part of the galactic material outside. It gets separated from the dark matter and they form ultra diffuse galaxies. So this is a very recent field of study, and people are still trying to find explanations as to why such kind of observations are being made. So all of this previous discussion, I hope I have been able to convince you that dark matter is real and that it exists. But what exactly is dark matter made of, right? Let us look at some of the properties that we can conclude based on the ideas that I have discussed just before. Dark matter may be machos. What is this macho? This is not the macho thing that we say as a compliment, right? This is not also El Macho from the Despicable Me movies, no. So macho is an abbreviation for massive and compact halo objects. So massive, why? Because they have mass and they exert gravity. Compact, because they are found in cluttered, they tend to clutter together, they tend to clump together. And halo, because generally we find dark matter, if there is a galaxy, we find that dark matter is surrounding it. We call this thing a halo, right? So this is one of the ideas, massive and compact halo objects. But what are these objects? We have ideas of what such massive and compact objects might be. So one of the explanations is that such massive and compact objects may be black holes, right? So some of you might recognize this is the recent image from the Event Horizon Telescope collaboration. So massive and compact halo objects might be black holes, but there are not enough black holes or primordial black hole candidates in the universe that can explain the amount of dark matter that we see in our observations using either galactic rotation curves or say using gravitational lensing. So MACOs can also be brown dwarfs. So you may ask me, sir, what is a brown dwarf? So a brown dwarf is basically something that is, too big to be a planet, yet too small to become a star. So brown dwarfs are, some tens of numbers of times more massive than, say, our own solar system planet Jupiter. They become so massive that they accumulate enough material to not be classified as planets, but they do not accumulate enough material so that their cores become hot enough to sustain fusion, right? So we have actually observed, and brown dwarfs are really, really hard to observe. So since I'm saying that we cannot see dark matter particles or what dark matter is, so people speculate that they might be dark objects like black holes or brown dwarfs, right? But dark matter can also be WIMPs, meaning weakly interacting massive particles. Again, weakly because they do not interact generally with other standard model fields, and also because they might interact using what is known as the electroweak interaction. Massive, again, because they have mass and they exert gravity. Let us reassess the situation. So based on all the previous discussion that I did, a suitable dark matter particle is neutral. It's electrically neutral. It does not interact with the electromagnetic field. It does not give off or interact with light or photons of light. It has little to none self-interaction. I have shown you actual physical measurements where we have seen galactic clusters colliding through each other. We have seen that the visible matter, it gets scattered off, but the dark matter, it remains where it passes right through each other, right? It has little to no self-interaction. It should be cold. Now, why it should be cold instead of hot has got to do with how fast it is moving. Because those of you who have, studied at least graduate level physics might know that temperature is nothing but how fast things are moving. It should be cold. It moves slow. And if you want to learn why it's called cold, it has got again to do with the cosmic microwave background and the early universe. I can go into that discussion. And it should be highly abundant, meaning everywhere we look in the universe, any galaxy that we look at, any galactic clusters that we look at, there is a dark matter halo that is present all around it. So these are the suitable properties for a dark matter candidate. Where can we look for such objects? So let us look again at the standard model of elementary particle physics. So I have once explained before what this thing is, what this thing is basically. This little guy over here is the latest edition. It is one of the first scalar bosons. Boson meaning, oh, by the way, it's named after which Indian physicist? You guys should know that. You should look it up. So this is the first scalar boson that was, discovered recently. So this standard model of elementary particle physics basically does not have any kind of particle that can match all of these properties. So people have been looking to modify the standard model. One of such proposals is sterile neutrinos, but some of you who are informed, who read about dark matter and dark energy, the question might pop into your mind that can neutrinos be, dark matter? They cannot be. There are compelling arguments why they cannot be. But there is another type of neutrino that is predicted that is called sterile neutrinos. But this thing has not been observed as of now. People have been developing billions of dollars of equipment to actually figure out if there are sterile neutrinos. They might be axions. I'll get into this thing. This is very, very interesting. They might be what we call SUSY particles. So you see, we physicists make up very good abbreviations, right? So SUSY basically means supersymmetry. So all of these things, they basically make up what we call the dark sector of the observable universe. A universe layered on top of our own that we have no particular way of observing, right? So the concept basically comes from quantum field theory. So our school knowledge tells us that there are forces. When you push something, it moves. There is gravity, there is potential energy, there is kinetic energy. But the advanced idea is that all of the things that we see happening all around us, they are basically inherently quantum in nature, and these different kinds of particles are described by different kinds of fields that are present all throughout space-time, right? Any kind of excitation to the vacuum state of these fields and you will get a particle. Say, for example, in a very simple term, you may consider that there is a field all throughout the universe for electrons, there is a field all throughout the universe for protons, and as we give, and as they get excited, as the vacuum state, the low energy state, as it gets excited, the excitations, they manifest as particles. So I would like to direct your attention toward axions for a moment, because this is something I find particularly intriguing, and this is something that I have, encountered in my own line of research. So as I have explained in a graphic before, the vacuum in quantum field theory, it's not boring like the classical vacuum. The classical vacuum, it tells you that if you have a box and if you suck out all of the air out of it using a pump, you get nothing, right? But the quantum description tells us that the vacuum itself is very energetic. It keeps on fluctuating. We would this little QCD thing that you see here is what is known as quantum chromodynamics. So this is a very fancy name, but in very simple terms, this particular theory, this QCD theory, it tells you how protons and neutrons are held together. So in case you didn't already know, protons and neutrons are made up of, in fact, even smaller particles which interact via other force-carrying particles. And this QCD theory, it tells you how these protons and neutrons are basically held together using all of these interactions, right? So the vacuum in quantum chromodynamics is very, very interesting. So when I say vacuum, I say that it is a state of lowest potential energy, meaning it is sitting at peace, it has got nothing to do, right? So usually the idea is that there is only one lowest energy state. There is only one vacuum, right? But the vacuum in QCD has infinitely many states. This potential energy here is a function of some variable called theta. So what this theta tells you is it includes a phase kind of a term into the theory, and depending on the value of theta that you put in, it has infinite number of vacuums. There is a big problem in particle physics that people are addressing that is called the CP problem. This is the charge and parity problem, right? Meaning the universe works more or less the same if it were mirror symmetric, right? So if you have a reflection going on in the entire universe, physical laws should look the same. Say, for example, if you flip the charges, a positive and the negative charge, they attract each other, right? So if you make the other one positive and the first one negative, they'll still attract each other. But as it turns out, when you consider these two symmetries together, and we physicists love to talk about symmetry in nature, when you consider these two symmetries together, and when you try to apply it into the QCD theory, it doesn't work out. There is a way to resolve this problem. The way to resolve this problem is this little guy over here. We can consider this to be a field. If we consider this to be a field, as was first done by Pecky and Queen, and as I have just told you, if you have any kind of field, you can quantize it, you can excite its vacuum state, and you can get a particle out of it, right? So if you quantize the theta field, you get a very peculiar particle known as the axion. And as it turns out, this axion has almost all the properties that are needed for it to be a suitable candidate for dark matter. Meaning, it has mass, it does not interact, and it is slow moving. But we have not been able to discover this as of now. People have been trying to discover this. We are still on the way. We have not figured it out yet. Also, there are supersymmetric particles. So supersymmetry is a very elegant theory, but it has not been proven yet observationally. So it tells you that all of the standard model particles, by the way, the standard model particles are either bosons or fermions, right? They have supersymmetric pairs. There are some supersymmetric particles, say for example, the neutralino, that can serve as dark matter candidate. These particles, they may have properties that make them suitable to serve as dark matter. So these are some of the very interesting ideas recently that are going on, and this axion field, basically it's particularly very, very interesting because it has some very interesting phenomena when we consider it in studies concerning black holes and wormholes, and in fact the universe as well. You may get a unified paradigm for dark energy and dark matter where they appear to be the same thing theoretically. There are lots of interesting stuff. We can get to this in the discussion if anyone has any questions. So we have nearly reached the end of my talk. So I would like to leave you with some interesting ideas, right? So if the universe is expanding, it is expanding at an accelerated rate, right? You may ask what is going to happen to the universe at the end of the day. So, but you can also ask the counter question. You may ask, what is it that happened at the very, very early universe? So you may ask, why is it that the dark energy constant, the cosmological constant, has this exact value that it should have? So that is where anthropic arguments come in, right? So it has that particular value because only if it has that particular value, then we can have a universe that looks like this. Then we can have a universe that forms stars like our sun, where planets like our Earth can form, where talking monkeys like us can sit and discuss why the universe is the way it is, right? So this is where anthropic argument comes in. There is another idea of inflation, or additionally eternal inflation. We did not go into this. My supervisor, Professor Deshmukhya, I have seen her in the audience. She is an expert in this topic. So eternal inflation is very interesting. It says that as the universe, was created out of the Big Bang, and as the space-time itself got expanded exponentially, it happened in pockets. Different pockets of the universe expanded at different rates. Different pockets of the universe does have different physical laws, and perhaps ours is one of the many multiverses that is out there, right? Also, one of the limitations of my talk today is that I have not gone through the detection part of dark matter, because already dark matter and dark energy is very, very difficult to include in one talk itself. And dark matter detection is another very, very technical and very intriguing aspect, which demands an additional lecture. Lastly, the universe keeps on expanding. What is it? What is it leading to? Will the universe expand so much in the far future that all of the atoms itself get ripped apart? Some of you might have heard about Big Rip. Or is some new mechanism going to kick in where the cosmological constant or dark energy does not remain dominant and the gravity becomes dominant and the universe contracts on itself? We might call it the big crunch. But recent ideas have suggested that before these timescales are reached, we may reach what is known as the heat death of the universe. So let us wind our clocks faster and faster and reach, trillions of years into the future. So in such a hypothetical scenario, what might happen is that all of the stars in the universe might have died off with supernovae. They might have formed black holes. And now we have good reason to believe that black holes, they evaporate away in time using what is known as the Hawking radiation. So all of these black holes might have evaporated away and there would be nothing remaining. The universe would absolutely die. There would be no energy left in the universe. This is the idea that I personally find very, very intriguing. It, compels me to think that this is what is going to happen. So does this indicate a cyclic universe? Meaning, does the death of one universe guarantee the creation of another? So this is an idea which was, the proponent of this idea is the very famous Sir Roger Penrose, and his idea is called conformal cyclic cosmology. The idea is very simple. So as the universe encounters a heat death, the vacuum becomes absolutely energyless. It doesn't become energyless. There will be fluctuations there. There is nothing remaining in the universe. There is no universe. There's total blackness. What happens is that the universe forgets its age itself. It forgets that it had started off with a Big Bang. It forgets that there is trillions of years of histories going on. When there is nothing left, these vacuum fluctuations that I have been talking about, they might spark off another new Big Bang and another new universe might start. And conformal cyclic cosmology says that this is a cycle that has been going on for all eternity and eons. Will we ever be able to answer these questions? I don't know. But these are questions that are worth answering, that are worth looking over. This is what makes your life more meaningful. As you look at the grandeur of the cosmos, it makes you realize how puny and little our insignificant human problems are. So with this, I would like to conclude my talk today. Thank you very much for listening to me.
Thank you, sir, for this wonderful presentation. Now I think we can move on to our Q&A session. So participants, if you have any questions, you can turn on your mic and ask your questions to sir directly, or also you can write in the chat and I'll read out the questions. Yes, Varsha, please You can ask your question.
Sir, I have a
Yeah,
question.
sure.
Sir, any proof of aliens was found?
No, not as of now, I'm afraid. So
Okay.
you may look at the Drake equation. You can Google it. So there is this very famous physicist who wrote down an equation using which you can calculate what is the probability of finding alien life. But as of now, we have not found. But I can tell you what we have found is potentially habitable planets, meaning planets orbiting other stars. We call them exoplanets that are very very similar to Earth, meaning they can have liquid water on their surface, they may possibly have oxygen on their atmospheres, and we know, right, that these are the things that are very very essential for life. So you might have heard that the James Webb Space Telescope has become operational recently, and using such telescopes in the future we will be able to measure what kind of compounds, chemicals, or gases are present in the atmospheres of exoplanets, right? And if there is life present, we expect to see some particular forms of gases using what we call spectrographic techniques. So, in the very near future, I personally believe that we will be nearing the answer to the question of are we alone in the universe? But as of now, no, we do not have any evidence of extraterrestrial life.
Sir, my
Hello,
question
sir.
is,
Yeah, hi, I can hear you guys.
sir, I am Vaibhav. My question is sir, that large galaxy cluster did bend the light.
Yeah. Yeah, it bends the light actually. Not just galaxy clusters, anything that is sufficiently massive. In fact, our star can be used as a our own star, our sun can be used as a gravitational lens. So if you try to learn what gravitational lensing is in very, very simple terms, if there is a very, very massive body that is present, and if there is a source of light that is coming from far behind, since this body is so massive, the light that is traveling, it will bend around it. Space-time itself is being curved because of the presence of this body, and the light will bend around it. So this is gravitational lensing, and this is what is used to observe or calculate how much matter is present in galactic clusters and things like that.
Sir, my another question is that in which thing that the universe is expanding.
Sorry, I didn't get your question.
So my question is that in which thing that the universe is expanding.
Well, that's a very good question, actually. We do not have any conclusive idea, but we say that the entire space-time that we live in was basically created with the Big Bang, right? Then you might end up asking, what is the universe actually expanding into? So we do not have a conclusive answer for that as of now, so far as I know. We have very very speculative, ideas, very very vague ideas, but I don't think we are able in a position to definitely comment on that as of
Hello, sir.
now. Yeah.
Sir, you told about the background radiation that we can see in infrared spectrum right now. So,
Mhm.
in there would be in a time where the background radiation was in visible spectrum. So, if hypothetically there were humans at that time, for them there would be no night. Can we say that?
Possibly, but then you have to consider the fact that when this light was actually in the visible range, the universe was not it had not cooled down enough for stars to form, let alone planets and creatures that can observe the light.
Okay, sir. And another question that can you tell a little bit more about the negative pressure that you told?
Okay. So let me go back to the initial slides. Yeah. So it is very difficult to explain intuitively. This is what we call relativistic scaling in very vague terms. So if you think about pressure, if you have a container and you have some gas that is inside of it, right? So common notion tells you that the pressure inside of the gas, it will push on the walls of the container, right? This is why when you punch a balloon with a pin, it explodes, right? So this is normal positive pressure. So if you have it inside of a container, it exerts a force on the walls. So if this pressure is negative, I would explain that the opposite thing happens, right? So if positive pressure, if it repels, if it expands, then negative pressure should contract. But although mathematically, when we calculate, although this PD term, although it becomes negative, when we consider relativistic effects, meaning when we integrate or add up this effect over long distances, it in the end ends up expanding the universe instead of contracting, although it is negative. So it is very, very hard to believe intuitively, and it is more difficult to explain without using mathematics, but that is the very basic idea. If you have negative pressure, you expect that it will contract. But when you consider scales as large as the universe, it has the opposite effect in case of dark energy.
Yes, Lena, please ask your question. Okay, so we have got a question in the chat. Okay, so we have got a question which is sound doesn't travel in vacuum. Then how do we hear sound of the sun or universe?
We do not hear the sound of this universe or the sun. You are right, it doesn't travel in vacuum. If this question is coming from my explanation of baryon acoustic oscillations, so sound is a term that we use. It is an acoustic oscillation, meaning it's a physical wave. So at that time, it was actually a sound wave in the very early universe, but alas, there was nothing to hear it. We do not hear the universe. That's not right.
Okay, so Brahmadev have asked, is white hole in celestial existence?
No. The white holes do not exist. You can do some funny bit of mathematics and you can write a solution to the Einstein's equation that looks like a white hole, but that will not be possible physically. We say that these are geodesically incomplete, meaning if you try to draw a path of a light ray or of anything through that space-time, it doesn't have anywhere to go after a particular point that we call the coordinate singularity. So no.
Okay, so Najib have asked, are we able to calculate or get some average figure for the big crunch by the calculation of the expansion of the dark energy?
Okay, hi Najib, it's nice to see you here. So no, I mean, we do not know for sure that if there is going to be a big crunch, right? So this dark and this cosmological constant thing, we have very good reason to believe that uh, it might not be constant, right? But as of now, all of our physical measurements have shown that the energy density of the vacuum is constant. In fact, I should have mentioned it when someone asked about the negative pressure thing. It's a consequences of the fact that the energy density of the vacuum itself is constant. But if you want to calculate when this big crunch is going to occur, we do not know if it is going to occur in the first place. So recently, we have very good reason to believe that the universe will go into heat death before all of that happens. So no.
Okay, so Vaibhav Pandey have asked, sir, what is anti-gravity?
There is no force or field that we can write down and say that this is particularly anti-gravity. So we encounter effects that look like anti-gravity, like the equations that they showed for dark energy, right? Gravity tends to pull the universe together, dark energy tends to push it outward. That is kind of an anti-gravity effect. There is no such particular thing as an anti-gravity substance.
Okay, so Lena have asked, what is black hole? I'd request you if you can give a brief description about it.
What is a black hole? So black holes, very basically, if you Google and find out what it means, is that it's a region of space where nothing can escape, not even light can escape, right? So what happens is that when massive stars they die, they collapse on themselves. So there is what is known as a singularity that is formed, meaning the star collapses into a point of infinite density, right? All known laws of physics break down. We don't know how the physics works in a singularity. And this singularity is surrounded by a spherical surface. We call that surface the event horizon. So this particular horizon, if you cross it, the gravity becomes so strong that Even if you're traveling at the speed of light, which is impossible by the way, you will not be able to escape. This particular structure of a singularity surrounded by an event horizon is what we call a black hole.
Thank you, sir.
Welcome.
Okay, so Sumed have asked, sir, can we also use Jupiter or Saturn as gravitational lens?
That's quite an interesting question, actually. So that would be gravitational micro lensing, right? But there are lots of factors at play. You can calculate out the position. It depends upon what is it that you're trying to see, right? So if there, usually we use gravitational lensing to see things that are very, very far away from our own solar system. And the mass of the planetary body that you're considering, it should be able to amplify or magnify that light significantly enough. So depends on what you are trying to observe. Possibly something as massive as Jupiter or Saturn may be used as a gravitational micro lens.
Okay, so in our YouTube chat, Rajeshwari have asked, sir, are there any books that you can suggest about related to dark matter or dark energy?
There are technical books that I may recommend, but there are books that can read. Card Orwell's book. Okay, whoever has asked me the question, please ping me in my email. I'll definitely send you some links. So I can give you physics textbooks, but since you don't require that, I'll have to look it up, and I'll definitely be happy to write back to you.
Okay, so Vaibhav asked, sir, how supermassive black holes are formed?
That's a very, very active area of study. It's kind of a mystery. We have good reason to believe that supermassive black holes, they form, as smaller black holes, they coalesce, they attract each other, and they merge and they combine, and they grow bigger and bigger in size. But so far as I know, there is no definite mechanism that we have formulated regarding how supermassive black holes they form.
Yes, sir.
Okay, so Neeraj have asked, sir, what is the difference between eternally collapsing objects and a black hole?
So eternally collapsing object is something that our Indian physicist, I'm forgetting his name. So one of the famous Indian physicists, controversial ones, in fact. So he has proposed something called Abhas Mitra. Yes. So he has proposed something called magnetospheric eternally collapsing objects. So the main difference is that if you have an object that is eternally collapsing, it might, and that does not have a singularity, meaning a point of infinite density where the known laws of physics breaks down. So you might describe what black holes are or what black hole like objects are without having to write down an entirely new theory of gravity. But the exact mathematical structure, I'm not quite sure. How is it different? The main difference is that there are no singularities. That's as far as I know. But I would also like to tell you that all of the observations that we have made, there is a very, very good confidence of saying that these things are actually black holes that are predicted by general relativity instead of anything else.
Hello, sir.
Yeah.
Sir, my son is Hemant Kumar, and he cannot understand English properly. So, can he ask you the question in Hindi?
हाँ जरूर जरूर कोई दिक्कत है नहीं.
सर सर नमस्ते
नमस्ते बेटा.
सर पहले मार्स पे जीवन था या नहीं
सॉरी.
ये कह रहा है सर कि मार्स प्लेनेट पे क्या पहले लाइफ एग्जिस्ट करती थी या नहीं?
मार्स में जीवन, हाँ हाँ, नहीं नहीं, पहले हो, मतलब अभी देखो बेटा, साइंटिस्ट लोगों को ऐसे ही बहुत सारी चीजें मिली है जिससे पता लगा है कि मार्स में पहले जल हुआ करता था, पानी हुआ करता था. अभी हमें मालूम है कि मार्स में पहले बड़े बड़े सागर हुआ करते थे, जैसे हमारे अर्थ में है ना. पर मार्स में जीवन था कि नहीं, वो अभी तक श्योरली पता नहीं चला है। हमें यकीन है कि हुआ होगा, पर अभी तक श्योरली पता लगा है नहीं कि पहले हुआ करता था वहां।
Yes, sir. Thank you, sir.
वेलकम।
Hello, sir.
Sir,
या
Hello, sir. Sir, so there were three equations that you saw K. So if K can have more than three solutions, then can there be possibility of more than one universe? And if possibility, then how can we get to know that there are more than one universe?
K does not have more than 3 solutions. So
So
if
you
you,
so that 0 plus and minus 1. So
yeah,
so this three. So if this three also, then like if we are 0, then how can we know that there are 1 and minus 1? How did we measure it?
okay, so if I'm understanding your question correctly, there are various ways in which we can measure the, or estimate the geometry of the universe. One of such ways is the what we call the cosmic distance ladder method, where we measure how far something is from us, and where we measure what is known as the angular distance of that object from us. And using such measurement techniques, we have very good confidence to believe that, to say that K is very, very nearly zero, meaning that the universe is flat. In fact, the entire modern cosmology is based on some very fundamental principles of cosmology. And one of them basically tells you that the universe is flat. The other to tell you that the universe is homogeneous and isotropic.
Okay, sir. So we know about our universe, but we know that we are nearly to 0. So that how did we calculate that there would be a universe that has plus or minus 1?
There
Like
may
we
be,
know
but
of R.
so we do not know for sure if there are other universes, right? So ideas like inflation that tell you that there may be other universes, they have not been tested yet. They have not been proven yet. So as of now, this is the only universe that we know of. Now, of course, there are regions of the universe that are causally disconnected from each other, meaning they have expanded so far away that no signals can reach us from that particular point. So these causally disconnected regions of the universe, they might have some different physics going on, which we do not know. But as of now, we do not know if there are any universes where the K value can be different.
Okay, sir. Thank
sir,
you.
Yeah, hi.
sir, ब्लैक होल की बेसिक कैलकुलेशंस क्या है?
आप कौन सी कक्षा में पढ़ते हो बेटा?
मैं 9th.
9th में, ओके। तो आपने न्यूटन्स लॉज तो पढ़ा होगा अच्छे से।
हाँ.
सो न्यूटन्स लॉज को अगर मैं उसकी और करेक्ट फॉर्म में लिखूं तो वो आइंस्टाइन की इक्वेशन बन जाती है। तो आइंस्टाइन की इक्वेशन को मैं जब सॉल्व करूंगा तो जो सबसे सिंपल वाला सोल्यूशन मुझे मिलेगा, वो सोल्यूशन एक ब्लैक होल डिस्क्राइब करता है। वो कैसे करता है वो जानने के लिए थोड़ा और हमें पढ़ना पड़ेगा मैथमेटिक्स उसके लिए, पर न्यूटोनियन ग्रेविटी के एनालॉग से भी हम ब्लैक होल टाइप की चीज बना सकते हैं मैथमेटिकली। पेन पेपर होता तो मैं आपको करके दिखाता, पर अगर आप मुझे बाद में मेल करो तो आई कैन show you the Newtonian analog of what a classical black hole would look like. So the
Okay,
basic
sir.
calculation for it is the basic calculations that are required are basically what we call differential geometry. डिफरेंशियल ज्योमेट्री की कैलकुलेशन से आइंस्टाइन की इक्वेशन लिखे जाते हैं, उसके सॉल्यूशंस निकाले जाते हैं।
Thank you, sir.
Hello, good evening, sir.
हाय, गुड इवनिंग।
Sir, my name is Krishna Kumar, I read in class 11th. My question is, how we know black hole exist?
So we didn't know for a long time if black holes do exist, in fact. So in 1971 we observed in the universe something known as a very, very high energy X-ray source, जिसका नाम Cygnus X1 था. So that was the first evidence of a black hole. It was releasing such high energy X-rays that it would only be possible if there is something very, very massive at the center that is driving the gases around it at such high velocities that it's emitting so high energies. Pehla proof. Secondly, we have observed the centers of galaxies, our own galaxy, of other galaxies, and we found that the rate at which the stars move around the centers of the galaxies, that can only be explained if something very, very massive and having the properties of black holes they exist. Number two, ho gaya. Number three, we have seen different astrophysical stuff like blazars and quasars. Sometimes they have a black hole companion, जिसकी वजह से observations होती है. Or very recently, तो we have directly imaged the shadow of a black hole. So all of these things they tell you that black holes they do actually exist in space.
सर साइंटिस्ट डार्क मैटर और डार्क एनर्जी को कैसे स्टडी करते हैं?
डार्क एनर्जी को बेटा कैसे स्टडी करते हैं हमने अभी बताया था हमारे प्रेजेंटेशन में. आप ये रिकॉर्डिंग यूट्यूब में बाद में सुनोगे तो आपको ध्यान से समझ आएगा. और डार्क मैटर को तो डार्क मैटर क्यों है कैसे है वो भी हमने डिस्कस किया ही है. और डार्क मैटर को कैसे डिटेक्ट करते हैं वो तो एक बहुत बड़ा अलग टॉपिक है. वो आप होपफुली हम लोग किसी और डिस्कशन में बैठ के ये बात कर सकते हैं. बट देयर आर टेक्निक्स.
सर जैसे बोला जाता है कि ब्लैक होल ब्लैक होता है, तो साइंटिस्ट उसकी स्टडी कैसे करते हैं, उसकी पोजीशन कैसे पता करते हैं कि वो कहाँ पे है? क्योंकि वो डार्क है तो स्पेस में वो दिखेगा नहीं ब्लैक होल.
तो ब्लैक होल डार्क है वो दिखता है नहीं, पर क्या होता है कि जब ब्लैक होल के आसपास दूसरे तारे होते हैं तो वो उसका मैटर खींचना शुरू कर देते हैं. तो इसके वजह से क्या होता है कि वो दूसरे स्टार का जो मटेरियल है वो ब्लैक होल के चारों ओर ऑर्बिट करने लगता है. और क्योंकि ग्रेविटी इतना स्ट्रांग है, ये ऑर्बिटल वेलोसिटी इतना बढ़ जाता है कि वो सारा गैस जो है वो रेडिएट करने लगता है, वो एनर्जी रिलीज करने लगता है. सो वो एनर्जी हमें ग्लोइंग लाइट की तरह दिखती है, जिसमें तुमको दिखेगा एक सर्कुलर रिंग है जिसमें बहुत ग्लो कर रहा है और बीच में सेंटर में कुछ है नहीं, पूरा काला है. तो दैट इज व्हाट इज नोन एज द ब्लैक होल शैडो. इवेंट होराइजन टेलीस्कोप ने रिसेंटली वही चीज देखी है. वैसे बहुत सारे तरीके होते हैं.
सर जैसे ब्लैक होल अगर हमारे सोलर सिस्टम के करीब आ जाए तो हम लोग को कैसे पता चलेगा? जैसे हम यूट्यूब में देखे थे ब्लैक होल के पास टाइम बहुत धीरे हो जाता है. अगर सन अगर ब्लैक होल में जाए तो वो हमें कैसे पता चलेगा?
तो हमारे सोलर सिस्टम के पास आएगा नहीं, बहुत प्रोबेबिलिटी कम है. कैसे होता है, क्यों होता है? और ब्लैक होल के पास टाइम थम जाता है, वो सही बात है. थम नहीं जाता या स्लो हो जाता है, इसको हम लोग टाइम डायलेशन कहते हैं. तो अगर आप टाइम डायलेशन क्या है अगर आप पढ़ो, ग्रेविटेशनल टाइम डायलेशन क्या है अगर आप पढ़ो, तो आपको ये चीज ढंग से समझ आएगा.
थैंक यू सर.
Okay, so Brahmadev have asked, sir, can Alcubierre warp drive possibly come into existence after a few decades?
Alcubierre's warp drive is a very nice mathematical trick, but we do not know how to manipulate space-time. We do not know how to manipulate gravity. So it's very, very far away in the future. Like one of these ways would be to harness the vacuum energy if possible. But current physics tells us that all of the known technology that we have, perhaps that we can predict, in fact, even 100 years in the future, they will not be able to meaningfully extract any energy out of the space-time vacuum. Or in other words, to be able to manipulate the geometry of space-time, or in other words, to make something that looks like a Alcubierre warp drive.
Okay, so participants, if you have any other questions, please feel free to ask your questions.
सर जी मुझे एक पूछना था अंशुमन सर. जैसे गैलेक्सी के सेंटर में एक मेगा ब्लैक होल होता है जो कि मैंने काफी डॉक्यूमेंट्रीज में देखा है या पढ़ा है
जी.
तो सर जी मुझे ये कहना मतलब पूछना ये था कि अगर हम लोग ये देखें कि स्टर्डिटी जो है किसी भी गैलेक्सी की, तो क्या वो एक जो मैसिव ब्लैक होल उसके सेंटर में क्या वो उसकी स्टर्डिटी बनाए रखता है, ऐसा कुछ है सर?
क्या वो उसकी स्टेबिलिटी बनाए रखता है, वो पूछ रहे हैं आप?
जी जी जी
जी देखिए, वो क्वेश्चन बहुत सही है आपका. एक्टिव गैलेक्टिक न्यूक्लिया हम लोग उन्हें कहते हैं, और उनके बीच में एक्टिव नहीं भी हो सकते कोई, पर गैलेक्टिक न्यूक्लिया में सुपरमैसिव ब्लैक होल्स होते हैं. और वेरी वेरी रिसेंटली इनफैक्ट कुछ ऐसी चीजें हमें जानने को मिली है जिससे ये पता लगता है कि दिस गैलेक्टिक न्यूक्लिया एंड दिस सुपरमैसिव ब्लैक होल्स आर एक्चुअली वेरी वेरी इंपॉर्टेंट फॉर द स्टार फॉर्मेशन प्रोसेस। गैलेक्सी की स्टेबिलिटी को ये इफेक्ट डायरेक्टली नहीं भी कर सकते बिकॉज देयर आर एलिप्टिकल और बार्ड गैलेक्सीज जिसमें सुपरमैसिव ब्लैक होल सेंटर में नहीं भी हो सकती है, वी डोंट नो फॉर श्योर। बट इन केस ऑफ गैलेक्सीज लाइक आवर ओन मिल्की वे की तरह स्पाइरल गैलेक्सीज में ऐसे सुपरमैसिव ब्लैक होल्स का सेंटर पे होना बहुत जरूरी है, क्योंकि दिस सुपरमैसिव ब्लैक होल्स दे turn the galactic neighborhood around them very very active. Due to that, star formation वहां पे बहुत बढ़ जाता है। But at the same time, over time, older stars they tend to accrete clump more towards the galactic center. As a result, वहां पे ज्यादा supernova explosion type की चीजें भी होते हैं। But if you think about planets, stars like our sun and planets like our Earth, we are in a relatively quiet galactic neighborhood. जैसे कि आपने एक्सोप्लैनेट्स के टर्म में सुना होगा कि हम लोग हैबिटेबल जोन की बात करते हैं कि स्टार्स के आसपास कैसी ऐसी जगह है जिसमें लिक्विड पानी वाटर रह सकता है, राइट। तो आजकल हम लोग गैलेक्टिक हैबिटेबल जोन्स की बात करते हैं जहां पे सन लाइक स्टार्स फॉर्म हो सकते हैं, जहां पे रिलेटिवली वायलेंट इवेंट्स इतने नहीं होते कि अगर किसी प्लेनेट पे लाइफ फॉर्म हो गया तो उसको डिस्ट्रॉय कर दे डेवलप होने से पहले ही। सो इन ऐसी फैक्टर्स पे ये सुपरमैसिव ब्लैक होल्स का बहुत इफेक्ट रहता है।
अच्छा, और इनको हम स्टार फैक्ट्री भी कह सकते हैं क्या फिर?
स्टार फॉर्मेशन तो हर जगह होती रहती है। देयर आर डिफरेंट रीजन्स इन द गैलेक्सी वेयर स्टार फॉर्मेशन हैपेंस, बट रीजन्स दैट आर नियरर टू मैसिव सुपरमैसिव ब्लैक होल्स एट द सेंटर ऑफ द गैलेक्सी, वहां पे ज्यादा एक्टिविटीज होती रहती है। वहां पे स्टार्स क्रिएट होते हैं, इजेक्ट होकर बाहर चले जाते हैं, पर ऐसा जरूरी है नहीं कि बस उसी जगह पे स्टार फॉर्मेशन होता है। स्टार फॉर्मेशन हैपेंस इन प्लैनेटरी नेबुला एंड इन सुपरमैसिव गैस क्लस्टर्स। इट हैपेंस एट डिफरेंट प्लेसेस थ्रू द गैलेक्सी।
राइट सर। और सर जी, एक डॉक्यूमेंट्री में मैंने एक और चीज देखी थी, मतलब जो एज अ साइंस फिक्शन, जो एज लाइक वो है, मतलब उन्होंने एक बताया था कि मतलब एक जगह पे उन्होंने एक ऐसी वेव देखी है, इनविजिबल वेव है, जिसे डार्क एनर्जी के फॉर्म में देखा जा सकता है, लेकिन वो वेव इतनी मतलब पावरफुल है कि उसके सामने कोई मटेरियल टिक नहीं पाता है, और जैसे ही वो कांच जहाँ से गुजरती है वहां से वो पूरा सब कुछ डिस्ट्रॉय करते चलती है, एज लाइक मतलब ये देखा गया था। तो ऐसा कोई आपके इसमें आया है सर कुछ स्टडी में?
जी, मेरे नॉलेज में ऐसा है नहीं। कुछ हो तो बाद में आप मुझे रेफरेंस के साथ मेल कर सकते हो। आई विल बी हैप्पी टू गेट बैक टू यू।
सर थैंक यू।
Okay, so we're really sorry we are running out of time, so we have to end our session here for today. So firstly, thank you Anshuman sir for conducting this session with us and giving us your time and helping us conducting this session and helping all our students with this, all our participants with this topic. And also secondly, I would like to thank SS Citizen Science Group and Kalimpong Science Centre for collaborating with us in conducting this session and helping us in conducting this session. And also, lastly, I would really like to thank all our participants for joining us today and making this session a successful one. Lastly, I would like to request everyone to turn on their camera once so that we can take a picture. Thank you, everyone. And with that, I think we can end our session here for today.
Thank you very much.
Thank you sir.
Sir, can we get your email so we can send you the doubts?
Thank you, sir. Bye, sir.
Take care.